Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at algebraic numbers. But in order to understand them, we need to know about polynomials. So a polynomial is a special type of map that is always a function. So it's a function that maps the real numbers onto itself. It takes a real number and returns another real number. So the input into this function we call x, and the rule as to which number the function returns is given here. It's a whole heap of terms, and each term is either a constant or it's an x with a natural number as the power. So that's what a polynomial is, and polynomials come up everywhere in maths. So it's really important, this idea of the root of a polynomial, because that's how we solve polynomial equations. So the root of a polynomial is a number that's mapped to 0. In other words, if a is a root of the polynomial, then f of a is equal to 0. So for example, fx equals x to the power of 4 minus 4x squared minus 5, that is an example of a polynomial. So I, the square root of minus 1, is actually a root of this polynomial. Why is that? Because if I substitute x for I, the square root of minus 1, I get this. So I to the power of 4 is 1. Remember, I squared is minus 1. That's the definition. So I get 1 plus 4 minus 5. So 1 plus 4 minus 5 is obviously 0. So I is a root of this polynomial. It turns out the square root of 5 is also a root of this polynomial. So the square root of 5, if you substitute this for x, square root of 5 to the power of 4 is 25. The square root of 5 squared is 5. So I get 25 minus 4 times 5 minus 5, which is 0. So note, even though this polynomial, it only had integer coefficients, so the coefficients are numbers in front of, the coefficients here are 1, -4, -5. Even though its coefficients were integers, it had a root that's a complex number and another root that's an irrational number. And it turns out that can happen all the time. So this brings us to the idea of an algebraic number. A number is said to be algebraic if it is the root of a polynomial with rational coefficients. So in the previous slide, the polynomial we saw had integer coefficients. All integers are rationals, so it had rational coefficients. So a number that is not algebraic is said to be transcendental. So we just saw on the previous slide an example of a polynomial with integer coefficients that had root 5 and I as roots. So these two numbers must be algebraic because they are the roots of a polynomial with integer coefficients. An example of a number that's transcendental would be something like pi. There's no polynomial with rational coefficients where pi is a root. In other words, there's none of those types of maps that map pi to the number 0. So by definition, all rational numbers are algebraic. So why is that? Well, let a be some rational number. Well, a is going to be the root of the polynomial x minus a. So it turns out this is a polynomial. The coefficient of x is 1, and this coefficient, the constant term, must be a rational number. So this is a polynomial with rational coefficients that has a as a root. It turns out it doesn't really matter whether you make algebraic numbers need to be the root of a polynomial with rational or integer coefficients. Because if you multiply a polynomial by a constant, you don't change its root. So for example, we know that a half is the root of x minus a half. But if I multiply each of these terms by, say, 2, it won't change the root. I get 2x minus 1. So the number a half is the root of a polynomial here with rational coefficients, and that implies it is the root of a polynomial with integer coefficients. So all rational numbers must be algebraic because they'll be the root of a linear polynomial like this. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.